everyone. Today we're going to start acids and bases. This lesson I had you guys take notes on. It was quite a bit of information because a lot of it was background information or some cool information. So I'm going to go ahead in this video lesson and star the most important things you should have. So I would make sure to really highlight these in your notes or make sure you have them written down. So as a general introduction, taste is one of the five senses we use to experience the world around us. The sensation of sour is actually the response to acids in certain foods. When you eat a lemon or limes or grapefruit, you're often tasting the sour part of citric acid. Green apples and grapes, malic acid gives it the sour taste, and rhubarb oxalic acid gives it that taste. Now, acids and bases actually have several importance. In fact, when we did acid-base titrations, I had you look up several important ways that we use acids and bases in our everyday life. Some people said if you have an upset stomach, you take Tums to relieve your stomach acid. If you're brushing your teeth, sometimes those have different acid-base reactions to help whiten your teeth. If you're cooking, cooking is a big one that works with acids and bases. But there are numerous things around us, such as industrial processes, biological processes, and even environmental processes. So, how do we carve into microchips? How are we able to farmland? Things like that. So, section 1 is actually very brief, and it gives the definition of acids and bases through the sense of Arrhenius. So, from early days, scientists recognized that they have their own characteristics. We've talked about acids being a sour taste. But bases tend to have a bitter taste and they have a slippery feel like soap. Now, Arrhenius was a scientist who gave one way to describe acids and bases. And this isn't the only way to describe them, as we're going to see later on in the lesson. These two definitions are actually ones I would have written in your notes. So I'm going to go ahead and star these. Arrhenius described an acid as something that whenever it's dissolved in water, it increases our hydrogen ion concentration. So typically most people say it's an acid if it has an H in it or a hydrogen. So here this has a hydrogen, hydrogen, and hydrogen. Specifically, those are hydrochloric acid, sulfuric acid, and phosphoric acid. A base, on the other hand, was described as whenever it's dissolved in water, it increases our hydroxide concentration, or OH. So our OH, remember, that's hydroxide. Things like sodium hydroxide and calcium hydroxide are going to increase this. So oftentimes people associate bases having an OH in them. Now, while acids can be described using that way, not every acid it can be described with that definition. In fact, it's useful, but it has limitations, and one of the biggest limitations is it's restricted to aqueous solutions. Everything that they described as an acid had to be dissolved in water. Instead of using that definition, Johannes Bronsted and Thomas Lowry independently and separately proposed a more general definition. Their concept is based on the fact that acid-base reactions usually involve a transfer of a hydrogen ion, and we can actually just call this a proton. Now, a hydrogen ion is just called a proton because if we look at hydrogen, its atomic number is 1. So it has one proton in it, one electron, and no neutrons. So if you make an ion and make that a hydrogen plus, you're going to get rid of the electrons. So you have 0 electrons, 0 neutrons, and 1 proton. So it's essentially just a proton. So we're going to look at an example to kind of explain what do I mean by a transfer of a hydrogen or a transfer of a proton. And we're going to look at a proton or an H plus in water. Let's focus on the chemical HCl. In water, if I dissolve HCl, it produces H plus ions and Cl negative ions. However, they don't stay as H plus and Cl minus. This hydrogen is positively charged and it wants to interact with oxygen atoms on water molecules. So water molecules, if you remember back all the way to chemistry, have a Lewis dot structure of 2 hydrogen but 2 lone pairs. These electrons are negatively charged, and so this positive charged hydrogen is going to want to attract to the water. So what happens is that hydrogen ends up bonding with the water. Instead of having H2O, it becomes H3O plus. So you can write the equation of HCl plus water can actually form H3O plus, which is hydronium, plus Cl negative. Now, you might be, well, where's the H plus concentration? It didn't increase it, but it did. H plus and H3O plus are used interchangeably to represent a proton. Now, H plus, we use that often, but H3O plus actually more closely represents reality. So sticking with that same example, let's talk about it a little bit more. Remember, our equation was as follows. We said that when water and hydrochloric acid mix, it forms hydronium and a chloride ion. And so that comes into, we've donated an H plus, we've donated a proton. This chlorine went from having a hydrogen to not having a hydrogen. It donated it or gave it away. So HCl is going to be our acid. Acids donate. H2O is going to be our base because if we look at it, water actually gained a hydrogen. So if it accepts a proton or a hydrogen, it's going to be our base. So notice we have our acid and our base. I'm going to go ahead and star this because this is a very good definition of Bronsted-Lowry acids and bases, whether it gives it away or it accepts it. This is an awesome way to define acids and bases because it means that not everything has to be dissolved in an aqueous solution. We can just look at, well, what happens to the proton? So, for example, during the reaction between gases, HCl is a gas and it reacts with NH3. And very briefly, it's going to actually make Cl negative and NH4 plus ions. Then those eventually fuse to make a solid. But what happens in this intermediate phase is you're going to notice that chlorine loses a hydrogen or it loses a proton. So since it's donating that, HCl tends to be our acid. NH3, look at it, it tends to gain a hydrogen. So since it's gaining or accepting a hydrogen, NH3 tends to be our base. Now, for an acid-base reaction to work, if we have an acid, we have to have a base to accept it. So they always work together. You don't have an acid if you don't have a base to accept it. So here with our definition of Bronsted-Lowry, an acid is something that must have a hydrogen atom in it so it can lose an H plus ion. So here we're losing hydrogen. A base tends to bind to hydrogen, or in other words, gain an H plus. Some things, though, can act as both an acid and a base, depending on the situation that it's put in. So substances that are capable of being both are called amphiprotic. Amphi is usually an abbreviation that's given to mean both. Like if you think of amphibians, they live in both water and land. So amphiprotic means it can give a proton or take a proton. Things that are amphiprotic are things like water, bicarbonate ions, bisulfate ions, etc. Depending on their situation, they can act as a base if there was something that's pretty acidic, or they can act as an acid if there's something more basic than itself. So here I found this picture that shows two situations with water. So this is going to be reaction 1, and this one's reaction 2. Notice that they both have water. In the first one, it's saying water acts as an acid, and the second one, it's showing that it's acting as a base. So let's take a little bit closer look at this. Here we have it as an acid. So remember, acids donate. So acids donate in hydrogen. So you're going to see this hydrogen, one of those, leave. So the H2O becomes an OH because I'm getting rid of one of the hydrogen. It's going to give the hydrogen over to our base. And this is a base because here I have one hydrogen and it turns into having 2. So that gets a 2. So that means that this is our base. Down here, water can act as a base by gaining electrons. Or protons. So bases gain an H+. So notice I went from having 2 hydrogen over here to having 3. This is an acid because it lost or donated its hydrogen. So here I have an H, but when I come over here, I don't have an H. Now that we've kind of identified, well, what's an acid and a base, let's talk about a conjugate acid-base pairs. Well, this is defined as an acid or a base such that our acid and our anion differ only in the presence or absence of a proton. Here's one thing I want you to know. Every acid has a conjugate base. And the other thing I want you to know is every base has a conjugate acid. So I'm going to go back to this previous problem. Here's my base. Notice that it turns into a conjugate acid because if I were to reverse this reaction, this one would have to donate. Notice the water is an acid, but the other side, it becomes a conjugate base. So we're going to work on being able to write conjugate acids and conjugate bases. So notice they're opposites. If you have an acid, you're making a conjugate base. If you are a base, you're going to make a conjugate acid. So here it's asking, what is a conjugate base? If you were given HClO4. Well, if I'm finding my conjugate base, that means everything over here are acids. And so acids, if we look at our definition, love to donate protons. So we're going to actually donate this proton here. There are 2 things you have to change. The first thing you have to change is the hydrogen. The second thing to change is the charge on your molecule because hydrogens are positively charged. So here if I'm looking at HClO4, if I get rid of this hydrogen, I'm left with ClO4. This had a neutral charge of 0, but I lost one of my positively charged. So 0 minus 1 got me a -1 for my charge. And so here's my conjugate base. Here, if I get rid of one of these hydrogens, I'm left with just HS. I'm a neutral charge here, but I've lost a positive. So 0 minus 1 gives me a -1 charge. Here, pH 4. I have to lose one of these hydrogen. So you have a pH 3. I have a +1 charge here. So I lost a proton. So 1 minus 1 gives me 0. There's no charge on this one. And then HClO3, I'm going to lose my hydrogen, so I'm left with a ClO3, and this is a -1. Well, if I have a -1 and I lost one, -1 minus 1 gets me a -2. Here on this one, it's asking for conjugate acids. So if I have a conjugate acid, that means that I'm working with a base. All of these other are bases. And they're going to accept a hydrogen. So and when you do these, you have to look at the hydrogen and then make sure you change the charge. So here my Cn negative has to have an H. I still have a carbon, I still have a nitrogen. Then I look at this charge. Well, here I have a -1, but I gained something that's positive. So -1 plus 1 gives me a 0 for my charge. Here I have SO4 2 negative. So if I'm going to gain in hydrogen, so let's put a hydrogen, SO4, but I have to worry about this. If I have a -2, but I gained 1, that gets me a -1 charge. Here, I am going to have to gain a hydrogen. So I now have 3 hydrogen. I still have my O, and I need to add 1 over here to my charge. So I get a plus. Over here, I'm still adding a hydrogen. So instead of 1, I now have 2 hydrogen. I still have my CO3. And then my -1 charge. Since I added a hydrogen, I add, and that comes out to be 0. Here I'm going to add a hydrogen, so I have 2. I have an SO3. This is a -1, so I have to add 1 to that, and that balances out to be 0. Fluorine, if you add a hydrogen, and then 1 plus 1 gives me 0. So notice that you're adding a hydrogen, adding to the charge. Here, PO4, if you add a hydrogen, you get HPO4. I had a -3 charge. Well, if I add 1, that changes to a -2. And then last but not least, CO. If you add a hydrogen, you have HCO, but you get a +1, so I'm going to add 1 charge. If you're still struggling with these, make sure that you come in and we can go over them. The last thing that I want to add is this isn't in your notes, but I do have problems like this on your homework, so I kind of want to go over it. We're going to identify conjugate acids and bases and also identify the original acids and bases. So here, acids and bases are going to be located on the left of arrow. Conjugate acids and bases are going to be located on the right of the arrow. So you have to look at your reactants and see what happens to them. So here, if I have HCl, notice that my HCl, in order to get to Cl -1, has to lose a hydrogen. So if I look at my definitions, acids donate, bases gain. So if I lose one, I'm donating it. That makes HCl an acid. NH3, notice that it tends to gain a hydrogen. So if it's gaining a hydrogen, that makes this the base. Now remember, with conjugate acids and conjugate bases, they're opposites. So if this one is an acid, Cl negative is going to be my conjugate base. If NH3 is my base, that means ammonium, or NH4 plus, is going to be my conjugate acid. And the reason for that is if I needed to reverse this reaction, they would do the opposite. NH4 plus would give up a hydrogen, and chlorine would gain one. Down here, if you're looking at it, PO43 negative, to get over to here, I had to gain an H plus. So that makes this one my base. Here, I lost, so this one makes it my acid. So if this was my acid, the opposite would be my conjugate base. And if this is my base, the opposite would be my conjugate acid. And then on the last one, to see what happens, if you have an HSO4, in order to get over here, we have lost. So that's going to make this one my acid. From here to here, we have gained. So that's going to make that my base. Remember, it's the opposite. If this is my base, this is my conjugate acid. If this is my acid, this is going to be my conjugate base. And that's the end of today's lesson. Please make sure that you come in and ask questions if you have any issues, and I hope you guys have a good day.